and evening. Okay, our syllabus will be up to photodiode. Okay, PN photodiode will be there na, up to PN photodiode. PIN photodiode is not will be there in our syllabus. So up to photodiode it will be included. Okay, so read the all bits whatever it will be there in back side of book. Already you have book no physics book, so read the all bits. So whatever it will be there back side. Okay, I will also explain you some bits today and tomorrow also. Okay, I will go to the lesson today. So first of all I will take the attendance of the participants. So yesterday we discussed about the PIN diode. Okay, positive, intrinsic, negative diode. Okay, so what is the advantage of main advantage of PIN diode means width of the depletion layer will be increases. So compared to the normal PN diode, normal PN junction photodiode. So this PIN photodiode bandwidth, that depletion layer width will be increases. Okay, uh, and so one more thing. So one more important thing is so dark current. So compared to the PN photodiode, so dark current will be very small. Okay, so I will ask you one question. So why we will use this photodiode will be in reverse bias? So can you anyone tell? Photodiode. Okay, in forward bias also there will be current flow will be there if you apply the forward bias, but we are connecting photodiode in reverse bias. What is the reason? Okay, I will explain you. So what is the main reason means here? So if you will take either PIN diode or PN photodiode, in case of both, so if you apply the forward bias, if you apply the forward bias due to majority charge carriers, some current is flow through this circuit. Okay, so if you apply the reverse bias due to minority charge carriers, some current is flowing. Okay, whenever light instant on that, whenever instant on that photodiode, what happened? So some electron hole pairs will be generated due to the instant of photon. Due to the instant of photon, so due to the charge carriers, current is flowing. Okay, so if you want to measure the incident photon intensity. Okay, so what we have to do? We have to measure the how much of current flowing due to that charge carriers. Due to the charge carriers, whatever the charge carriers released, so because of the absorption of light. Okay, if you connect in forward bias, what happened? Already in forward bias there is a large amount of current will be there. Okay, so if you connect in forward bias means, so here photon will be instant and some carriers will be generated, so that due to the carriers, so current will be very small. Due to the generated carriers, so current will be very small compared to the majority charge carriers in forward bias. So that's why, so that variation of current we cannot observe. That variation of current we cannot observe. Understood? If you connect in forward bias, already in forward bias current, so diode current will be very high. Diode current will be very high. It will be in amperes. It will be in amperes or milliamperes. Okay. uh, Whenever light is fall on the photodiode, what happen? So charge carriers will be developed. So charge carriers will be produced. Due to that charge carriers, current is flow. Current will be flow. Okay, either it will be connected in forward bias or reverse bias. So depends on the bias that charge carriers will move. Charge carriers will move and current is passing. Already it will be there. So huge amount of current in forward bias. So due to this charge carriers, some amount of current is added, so that the added current is very small compared to the already existed current, in forward bias. That's why, so we cannot change the difference between the what is that initial current and so final current. We cannot find the difference between the initial current and final current. That's why, so photodiode does not connected in forward bias. Okay, so photodiode is connected in reverse bias. So for in case of photodiode, so due to minority charge carriers in reverse bias due to some minority charge carriers, there is a little amount of current flow will be there. Little amount of current flow will be there, but so that current flow will be in nanoamps or microamps. Nanoamps or microamps. Current flow will be so very small, very small. Okay, so now after light incidenting, some charge carriers will be developed. Due to that charge carriers, so compared to the current, we will call it as photocurrent. Due to photon absorption, some charge carriers will be developed. Due to that charge carriers, current will flow through this circuit. That current we will call it as photocurrent. Okay, compared to the dark current, whatever the initial current will be there, that is the dark current. Compared to the dark current, photocurrent will be high. Photocurrent will be high. So we can change the difference between the initial current and final current. Okay, that's why. So we are connecting here in reverse bias. Photodiode is we are connecting in reverse bias. That is the main reason why we are connecting the photodiode in reverse bias. Okay, I think you understood about this. So if you have any doubts on this, you can ask. Okay. Yeah. Now, so PN already PN diode, photodiode we discussed. So PIN photodiode means positive intrinsic negative diode. So due to that, yes. So due to this intrinsic region, what happened? So the width of the deposition layer will be increases. So that's why there is a large amount of area. So due to this intrinsic region, so what happened? So we will get the large amount of area. So to capture the photons. Here large amount of area is available to capture the photons. Okay, that's why what is that we can instant huge amount of light also. Huge amount of light also. So it will be detected. Huge intensity of light also. So by using photodiode, we can detect. We can detect. Okay, that is the main advantage of PIN diode, as well as due to minority charge carriers. In P region there are some minority charge carriers will be there. In N region there are some minority charge carriers will be there. So due to that minority charge carriers, so here current flowing through the circuit will be small, very small compared to PN photodiode, because here width of the deposition layer is so high. So in forward bias also, so that means for if you connect here positive terminal to the N region, negative terminal to the P region, so for minority charge carriers, this will be act as a forward bias. For minority charge carriers, so this connection will act as a forward bias, because here N region holes will be present. So that holes repelled by the positive terminal. Okay, so that hole should cross the this intrinsic region, so that's why it's needed much more voltage, because here width of the intrinsic region is very high. Okay, so that's why here applied voltage also very high, then only these minority charge carriers will cross the junction. Okay, so that's why at lower voltages. So in PIN diode, so we are applying maximum 5 volts only. Okay, 5 volts only. Okay, so that's why. So if you 5 volts applied means, so due to this minority charge carriers, there is no effect. Okay, that's why dark current also very small in case of PIN diode. Okay, now. Yeah. So already we know that. So whatever the construction, it will be the working construction. Okay. So construction. So while going to the construction here, so working is, so whenever light is incident on the, so this intrinsic region. Is nothing but here depulsion region. What happened? Charge carriers will be produces due to the charge carriers current flow through the circuit. That is the working here. Okay, so one more thing we have to observe here. So that energy of the incident photon, should be greater than the this uh, energy gap between the PN junction diode here. Energy gap between the PN junction diode. Okay, then only what happened? So here current will emit. Current will passes through the circuit, because if energy is greater than the energy gap of the semiconducting material, then only electron hole pair will be generated. Electron hole pair will be generated. That breaks the covalent bond. That breaks the covalent bond. If you are taking semiconducting material here, if you are taking semiconducting material, so energy gap of the semiconducting material will be, so suppose here 1.7 electron volts, 1.7 electron volts. Okay, so if incident light energy should be greater than the that 1.7 electron volts, then only here current passing through that circuit. Current passing through that circuit. Okay, so I will ask you one question. Suppose we are taking 4 electron, so here band gap of the this semiconductor is 4 electron volts. 4 electron volts. Okay, so what is the minimum wavelength required to observe that means to work the photodiode? So what is the minimum wavelength to incident to work the, otherwise to sense the photodiode? So can anyone tell the formula, which formula we have to use here? So energy gap is given 4 electron volts. Energy gap between the semiconductor device is given 4 electron volts. So we have to calculate the, so what is the minimum photon frequency, photon wavelength is required to sense the photodiode? Anyone? If you give the bit in this exam, so what you will write? Yes, anyone can answer. So we have to, and here energy gap is given, so lambda we have to calculate. Which formula we have to use? So are you there or not in class? I will ask you one by one. Okay, see here. So already we know that formula, energy gap between here, energy gaps. So energy gap of the semiconductor E is equal to H nu. Energy gap of the semiconductor E is equal to, formula will be H nu. So nu equal to that we have to calculate lambda. So that means this formula we have to convert into, so in terms of lambda. So that equal to E is equal to nu, means we can write C by lambda. So formula will be Hc by lambda. Hc by lambda. Already we know that Hc value, suppose in terms of micrometer. Okay, Hc value will be in terms of micrometer, means 12.4 micrometer. Okay, so otherwise nanometer means 12,400 nanometer. Okay, simply, so how, what we can write? E is equal to Hc by lambda. We have to calculate lambda value. So that's why lambda is equal to, we can write Hc by E. Hc by E. Okay, here E is in terms of electron volts. E is in terms of electron volts. So given value is, so 4 electron volts. 4 electron volts. Hc value is, already we know that. So suppose so we are calculating in nanometers. Nanometers means 12,400 Hc value. So 12,400 by 4. Okay, so whatever the it will get, so that is the value of lambda. Okay, so like that we have to calculate the, so which wavelength is required, which wavelength is required to work the this photodiode. So minimum wavelength is required to work the photodiode. Okay, so this is about the, so how to calculate that. Okay, now coming to the here. Here, so already we discussed about the working. Now in case of PIN diode, so how to prepare this PIN diode? How to prepare this PIN diode? I will explain you. So yesterday, so there are two ways are there. Two ways are there. So one is the planar structure, another one is the MESA structure. One is the planar structure, another one is the MESA structure. Okay. In case of planar structure, an epitaxial film is grown onto the substrate material. So what is the substrate material here? This is the intrinsic region. Intrinsic region means pure semiconductor. So pure semiconductor like silicon. Best one of the example is silicon. Silicon is the intrinsic semiconductor. So if you will take silicon is your substrate. Okay, on that silicon we are doping. So epitaxial N-type film. Epitaxial N-type film. Okay, epitaxial means so very thin film. Very thin film, that is crystally ordered film. Okay, crystally ordered film. That is the epitaxial film is grown on the so one region. So this side of the intrinsic semiconductor. Okay, and if you will take another side is p region is introduced. P region is introduced, so either by using diffusion technique or an implantation technique. Okay, if you want to use diffusion technique means so we have to use high temperatures. So at high temperatures we have to dope here trivalent material at another side of the intrinsic region. Okay, so but so for going high temperature every time is difficult, so that's why so another method is there, that is an implantation method. So this is the low temperature method. This is the low temperature method. So what is the this ion implantation means that accelerated ion interact with the this substrate. Either chemical and physical reaction will be occur here. Chemical or physical reaction will be occur. So due to that physical and chemical reaction, so there will be another layer will be formed. Okay, that is the p layer. Okay, so this is in case of uh, planar structure. In case of planar structure, so by using planar structure, how to prepare? So PIN diode means, so this is the one way. So next one is the MESA structure. Okay, MESA structure has, so this also layer structure. So layer structure. So if you will take same silicon substrate here, that is the intrinsic substrate, and that intrinsic substrate, so N layer as well as so P layer will be deposited. P layer will be deposited. So this is the controlled process. MESA structure is the controlled process. That's why, so by using this MESA structure, we can control the so width of the layers. That's why, so if you control the width of the layer, automatically properties of the diode will be changes. Automatically properties of the diode will be changes. Okay, so what is those properties means? So here I explained here. So it reduces the fringing capacitance and inductance. As well as it improve the level of surface breakdown. Okay, so fringing capacitance means suddenly increasing of capacitance. So by overlapping the so two or more electric field. Okay, similarly inductance. So like that, so we can reduce the by using so this method MESA structure, we can reduce the that fringing capacitance as well as inductance. Okay, and surface breakdowns also. These are the so two ways of preparation methods. Okay, now here some more characteristics are there. The intrinsic layer gives properties such as high reverse breakdown voltage, and low level capacitance, and as a carrier storage when it is forward biased. Okay, so if you will take PIN diode, it is a intrinsic, it has intrinsic layer, so properties has high reverse breakdown voltage. So I told that, so why here reverse breakdown is high? So because so width of the deposition layer will be very high. So that's why, so here reverse breakdown voltage will be high. Okay, and if you will take in forward bias, so that forward bias capacitance level of the capacitance is low, and as well as so carrier storage. So that capacitance will be depends on carrier storage only. Okay, if you will store more carrier storage means it's have high capacitance. Okay, so that's why, so while using in forward bias, it's have low capacitance as well as carrier storage. Now when pi and diode is forward biased, both types of current carriers are injected into the intrinsic layer where they combine. It is it is this process that enables the current flow across the layer. So in case of forward bias also, current flowing through the circuit, because so at intrinsic region, so these electrons and holes are recombined with each other. So due to that region, so what happened, current flow through the circuit in forward bias. Okay, these are the some pi and diode characteristics. Okay, now so major applications, so high voltage rectifier. So this also pi and diode, we can also use it as a high voltage rectifier. So due to this intrinsic region provide greater separation between the p and n region. Okay, allowing higher voltage to be tolerated. So because of that separation, because of so that large separation between the p and n regions, so it will be used as a high reverse voltage. It will be used in high reverse voltage applications. That's why it will be used as so high voltage rectifier. Okay, next rf switch. rf okay, rf switch means radio frequency switch. So that means while tuning the particular frequency, so we can use this pin diode. If you want to particular frequency, so required radio frequency, by using pin diode we can switch. Because what is the reason how to switch means, here see here, so change here we can use the, so this pin diode. So by changing the so regions, p region and n region, width of the p regions and n regions, what we will change, so we can change the capacitance. Of the pin diode. You can change the capacitance of the pin diode. So whenever signals are passing through this capacitance, okay, so automatically, so these capacitance will control the particular, so it allows the particular frequency signals. So depends on the its capacitance. Suppose so signal is nothing but, so it will be converted, that signal is converted in the form of AC signals. AC signal means like AC current. Okay, AC current. So while passing through that current, so this capacitance controls depends on the width of the capacitance. Okay, depends on the width of the this pn regions. If pn regions will be, width will be increases means this capacitance will be increases. Width of the pn regions will be decreases means, so we can decrease the this capacitance. Okay, like that. So while varying the, so width of the p region and n region also, so distance between the p and n regions, we can change the capacitance of the pin diode. Okay, that's why we can use so this pin diode as a rf switch. Switch is nothing but, so it provide particular required frequency. Okay, so suppose radio is working. So radio is working means, so suppose if you want to change the radio channels, we can correlate that channel with a particular frequency. So how to correlate means by using so rf switch, radio frequency switch. Okay, so pin diode we can use as a rf switch. Okay, now photodetector. So already this is a so well established application of pin diode. Okay, so as the conversion of light into current takes place within the deposition region of a photodiode. Okay, increasing the deposition region by adding the intrinsic layer improves the performance of increasing the volume in which the light conversion occurs. So automatically, if you increase the width of the deposition layer, so what happened? we can increase the photodetector capacity. We can increase the photodetector capacity while increasing the width of the intrinsic region. So if you increase the width of the intrinsic region, automatically width of the depulsion layer will be increases. So that's why, so we can change the range of the photo detection. What is that? Some major applications of the PIN diode, and advantages of PIN diode. See here, the depulsion region is very wide. And extends throughout the intrinsic region. Okay, in case of PIN diode, so width of the depulsion region is high, and extends throughout the intrinsic region, and this will be so extended throughout the intrinsic region. Hence, the reverse bias need not to be wide in the depulsion region. Okay, so that's why already this width of the depulsion layer is very high, That's why, so no need to apply high reverse voltages. To increase the width of the potential barrier, width of the depulsion layer. Okay, so that is the one advantage. So what is that advantage? Means no need to apply the very high reverse bias voltages. Okay, so that is the one advantage. And so reverse bias applied is small. Okay, same above bit only. So in the order of 5 volts. So 5 volts is enough here for working of PIN diode. So less than 5 volts is enough. Okay, that is less than 5 volts also reverse biased voltage here. Okay, next point, as the depulsion area is wider, most of the incident photons are absorbed in this region, and hence efficiency of this device is high. Okay, so here it absorbs the most of the photons what it will be incident on. That's why, so efficiency will be very high. In case of PIN diode. And the next last point is the dark current in this device is smaller. I already explained you. So why dark current is small? I explain you. So this dark current in this device is smaller. Okay. Now some disadvantages. Of PIN diode. Okay. So less sensitivity in case of PIN diode. So sensitivity is less. Okay, and no internal gain. There is no internal gain, and small area. So compared to avalanche, okay, here we are comparing. So APD diode. That means avalanche photodiode. Okay, so compared to that, so it has small area and slow response time. Slow response time and high reverse recovery time due to power loss are significant. Okay, so these are the some disadvantages. So compared to the APD diode, avalanche photodiode. Okay, so these are, next class we will discuss about the this avalanche photodiode. Okay, so now we will discuss about some bits. Yeah, see here. Yes, is it visible? Anyone respond? So now PPT is visible.
Yes, sir.
Yeah. Okay. Yes. So we'll discuss first unit some questions here. So which of the following phenomena cannot be explained by the classical theory? Yes. Read everyone. So which phenomena is not explained by the classical theory? Anyone can answer. C1. C1. Respond once. C1. So already we discussed about the classical theory. Okay. So in that classical theory, so which effect, that means so what it does not explain. So Compton effect, is it explain the Compton effect?
Yes, sir.
Classical theory, not quantum theory. So classical theory does not explain the quantum Compton effect.
All of
As
the
well,
above, sir.
yes, all of the above. Okay, all of the above is the answer here. Okay.
All of the above, sir.
The Compton effect as well as photoelectric effect and Raman effect also. Okay. And so which of the following phenomena show the particle nature of light? Okay, already we discussed about the some phenomena. Okay, so the those phenomena, so in that some phenomena explains the so particle nature of light. So which phenomena? Interference.
Photoelectric effect, sir.
Yes, photoelectric effect. So very good. And next, so Wien's law is deduced from the Planck's radiation formula under the condition of. Okay, so already Planck's radiation law we discussed. So Wien's law, Rayleigh-Jeans law we discussed. Okay, so Wien's law works at here very small wavelength and temperature. Large wavelength and low temperatures. So which one is correct?
Large wavelength or high temperatures.
No. So Wien's law will explain only small wavelength. Small, very small wavelength and temperatures. Very small wavelength and temperatures. First one. Answer is so first one. Wien's law deduced from the Planck's radiation law under the condition of very small wavelength and temperatures. Okay. So now Rayleigh-Jeans law deduced from the Planck's radiation formula under the condition of. So what is the condition? So Rayleigh-Jeans law. So that is, so what is the Wien's law?
Large wavelengths.
Yeah, large wavelength and high
High
temperatures.
High
temperature.
temperature.
Yes. So large wavelength and high temperatures. Okay. So answer will be here B. Okay. Now, so which of the following characteristics photon have? So what is the characteristics of photon here? So for
M is equal to C,
H
sir.
nu, and so photon mass is equal to some L square. So all of these. So which one is correct?
D.
Sir,
So here h nu by c square amma. Here not appearing. Here h nu by c square photon energies. So here,
excuse me, sir.
so yes,
Sir, the C
yes, tell
is
me.
M is equal to C square means, sir, we told no, sir, that the
So
photon has.
yes, yes. So this is here, I think it is given wrong here. So here m equal to h nu by c square. So B option is m equal to h nu by c square, and so C option is E is equal to h nu. E is equal to h nu, and mass of the photon here first option is m equals 0. Okay, so which one is correct? So this is one is E is equal to h nu. The second one is m equal to h nu by c square. M equal to h nu by c
M.
h nu by c square. Here E is equal to h nu. Here printing is wrong. Okay. So which one is correct here? So photon, if you will take photon have, there is no mass. Okay, so mass of the photon is 0. That is correct only. And next one, so mass m e equal to mc square annam kada, e is equal to h nu. So m is equal to h nu by c square. M equal to h nu by c square. So that's why, so this also correct. And here one more formula, E is equal to h nu. E is equal to h nu. Okay, that is the three formulas here. Those three formulas are correct in case of light. So that's why all of these. Okay, here printing mistake. And next one, which are okay, what is the answer for this? So de Broglie wavelength. So what is the de Broglie wavelength formula? So
P is equal to H by lambdas.
so here option A is equal to h by 2m, h by 2m into qv. Okay, now option B is so h by under root of 2me. Okay, so option C is h by under root of 3mkt. Okay.
A is answer, sir.
Answer is h by under root of 2me. Answer is h by under root of 2me. Okay, that is the de Broglie wavelength. So if you will take in case of energy. Okay. So here not displaying in this. Okay, already, so the in PPT it will be good, but while presenting, so that whatever formulas will be there, those are not displaying here. The phase velocity of the de Broglie wave associated with an electron is, so phase velocity of de Broglie wave. So what is, the phase velocity? So phase velocity answer will be E by P. So phase velocity of the de Broglie wave is, so this is the answer here. Okay, answer is D. Okay, so next one. Electron behaves like a wave as it. Okay, so can be detected by electric field, can be detected by the crystal. Okay, so what is that? So already, so in one experiment, so we observed this. Okay, it's like behave like a wave. So electron is behave like a wave means, so what is the so what how we can find out that? By using nickel crystal. Okay, so by using nickel crystal, so what, so there is a diffraction here, so we can detect by a crystal, because so we are wave nature. So wave nature means, so wave does not affect the here electric field as well as magnetic field. So that's why, so by using this electric field and magnetic field, we cannot explain the wave nature of light, wave nature of electron. Okay, only so diffraction process. So now by using this crystal, diffracted crystal, so we can detect the electron as a wave. So that's why answer will be D. Okay, next, a material particle is in a thermal equilibrium at the temperature T. The wavelength of the de Broglie wave associated with it is, so what is the formula? Already you know that. So what is the de Broglie wavelength formula? So whatever the previous bit will be there, that here, so the wavelength will be de Broglie, lambda is
C,
equal to
sir.
the mid. Okay, So here I'll read that lambda is equal to, we know that h by p. So p will be in terms of either temperature. So that means so here in terms of t. Okay. So in terms of t means, so how we can write the, so p is equal to in terms of t. So that we have to know that. Okay. So that is the answer here. And next, photoelectric effect involves only, electric effect involves only free electron or bounded electron, both A and B, none of these. So what is the answer? Photoelectric effect. What is the definition of photoelectric effect? Definition: when light is instant on the metal plate, what happens? Those metal absorbs the light and it emits the electrons. Okay, so this is about the photoelectric effect definition. Okay, that's why what happened, so electron will become free, electron will become free. Okay, so remaining we will discuss on tomorrow. So I will take the attendance right now, so then we will go for the, yeah, so tomorrow we'll discuss about these answers. So read whatever backside will be there. So whatever, so in your back, yeah, textbook, in textbook backside there will be so many objective bits will be there. So read those all objective bits. Read those all objective bits. Okay. Yeah. So you can leave from the session.
Thank you, sir.